Roads, where we're going, we don't need roads. It's time for math with Mr. Troy. That's not a quote from The Matrix. That's back to the... All right, sometimes something neat happens when we're multiplying matrices together. You see, no matter which direction I multiply these matrices in, whether it's A times B, or if it's B times A, I get the same thing. 1, 0, 0, 1. Now, as you may already know, 1, 0, 0, 1 is called the identity matrix, specifically the 2 by 2 identity matrix. When you multiply it by a compatible matrix, something interesting happens. You see, no matter which direction you multiply in, you end up getting the same matrix that you multiplied by. As long as the multiplication is defined, the identity matrix will always multiply to return the same thing it multiplied against. No matter whether that's multiplying on the left or on the right. When two matrices multiply together to make the identity, they are called each other's inverses. We often use this notation a raised to the negative first power, which we're borrowing from multiplication, to represent the inverse matrix. So to demonstrate that two matrices are inverses of each other, we simply multiply them together. And if we arrive at the identity, we know that they are inverses. Let's take a look at this example. A times B would be 9 minus 8, that's 1. Negative 4 plus 4, that's 0. 18 minus 18, that's 0. And negative 8 plus 9, that's 1. Sometimes you'll be able to notice a pattern in inverses, but not every time because the pattern can be quite complicated. The identity for a 3 by 3 matrix has the same pattern with 1s on its main diagonal and 0s in every other place. Multiply A and B together to verify that they are inverses. You can pause the video and I'll wait here. So to summarize, we can tell that A and B are inverses because when we multiply them together, we get the identity matrix. This is a property for square matrices. So we wouldn't find the inverse of a 3 by 4 matrix. This is a reminder of an extremely important fact, that A times its inverse equals the identity matrix, and the inverse times A also equals the identity matrix. Since multiplication in matrices is in general not commutative, we need to make sure that we say both. Now, not all matrices have inverses. A non-invertible matrix is called a singular matrix, and a singular matrix is one that doesn't have an inverse. All three of these are singular matrices. Can you figure out what it is about these matrices that makes it so they aren't invertible? They have linear dependence. In the first one, it's pretty easy to see that the second row is 5 times the first row. In the third one, it's pretty easy to see that the two rows are the same. If you divide the top row of the middle matrix by -3, you get the bottom row. This is something that we saw when we were solving systems, and it's something that we'll see again when we're solving systems. To tell if a 2 by 2 matrix is invertible, we're going to calculate what's called the determinant. The determinant is sometimes written as DET or as straight vertical bars around the capital name or around the matrix. The way that you calculate the determinant is you multiply A times D minus B times C. Now this is a shortcut for the 2 by 2 matrix. So this helps us understand why our earlier examples didn't work. If your determinant is 0, then you end up dividing by 0, and it doesn't matter what you multiply by. Let's take a look back at those. In the first one, the determinant would be 1 times 15 minus 5 times 3, or 15 minus 15, or 0. So that shortcut for the matrix, for its inverse I should say, would be 1 over 0 times, who cares? You can't divide by 0. So a singular matrix has a determinant of 0. A matrix with a determinant of 0 is not invertible. A matrix that is not invertible has a determinant of 0. Give yourself bonus points if you can make it through the rest of the year without confusing determinant and discriminant. Oops, sorry for putting that in your head. So the rest of the formula to find the inverse of a 2 by 2 matrix has you multiply by this mixed up matrix. The name for this mixed up matrix is the adjugate, or what's sometimes called the classical adjoint. Not just the regular adjoint, the classical adjoint. Let's see this in effect. So the first thing that we want to do is we want to calculate the determinant. So the determinant of A, which is also written as A in vertical bars, which you'd think of as absolute value bars, is 3 times 2 minus negative 2 times negative 1, or 6 minus 2, which is 4. So we take that and we put that in the denominator, 1 over 4, and then we are going to multiply by the adjugate. Now, in case you didn't write it down, here's the formula for the adjugate. And the way that you find it is you switch the position of A and D, so the first and fourth elements, and you switch the signs of B and C, so change them from negative to positive or positive to negative. If you hadn't written that down, now would be a good time to pause the video and write it down. So we are going to switch the positions of A and D, and we are going to change the signs of B and C. Then we multiply our scalar in, and we're going to get 1/2, 1/4, 1/2, 3/4. The way that we test to see if that is in fact the inverse is that we take it and make sure that when we multiply the original matrix by it, we get our identity. So let's do that now. There's the supposed inverse that we just found, and we're going to multiply it by 3, negative 1, negative 2, 2. We get 3/2 minus 1/2. That's 2/2, or 1. We get negative 1/2 and 2/4, which adds to 0. 3/2 minus 3/2, which adds to 0. And negative 1/2 plus 3/2, which adds to 1. So you do the same for B. Make sure that you know how to find its determinant, its adjugate, its inverse, and then check that by multiplying together to make sure that you make the identity matrix. Now, the reason we care about inverses may not be immediately obvious. So for starters, we can write a system of equations as a matrix equation. Make sure you understand how this works. 1 times x plus 2 times y equals 13. 2 times x plus 3 times y equals 23. This is not merely an organizational technique, but is 100% consistent with all of the work that we've done so far. So 1x plus 2y is what we would get from multiplying the top row, and 2x plus 3y is what we would get by multiplying the bottom row. We learned that equal matrices have to have equal elements, which means that this element, 1x plus 2y, has to equal 13, and 2x plus 3y has to equal 23. So it's a way of representing a system. Now, the reason that that's useful is because now we can write our unknown as a variable in an equation. Not 2 variables in an equation, but 1 variable in an equation. The coefficient matrix times the variable matrix equals the constant matrix. Now the benefit of that is that if we multiply both sides of the equation by the inverse, then these two will multiply to make the identity. What happens when you multiply the identity by something? Well, you just get that thing. So what I'm saying is this. If you multiply by the inverse of the coefficient matrix on both sides, then the coefficient matrix and the inverse matrix will cancel out to make the identity. And your solutions can be found simply by multiplying on the left the inverse times the constant matrix. It takes solving a system from being something that takes steps and planning and intuition into just a matrix multiplication problem. So let's take a look at how you would solve this system using just matrices and inverses. So for starters, you're going to write your equation in matrices. Then you're going to find the inverse of your coefficient matrix. You'll need that to multiply against the constant matrix. Then you'll just multiply the inverse by the constant matrix, and your solutions will be there. Let's see all this in action. So first, we need to figure out, is this matrix invertible? So our determinant is 3 minus 4. That is invertible, that's -1. And we're going to multiply that by the adjugate, which is 3, -2, -2, 1. And then our inverse is -3, +2, +2, -1. It's important that you label these things because when they look similar, you're likely to get confused. Then all we have to do is take that inverse and multiply it by the constant matrix. So negative 39 plus 46, that's 7. And 26 minus 23, that's 3. What I'm saying is that I have just found that xy is 7, 3, meaning x is 7 and y is 3. Let's go take a look. 7 plus 6 is 13. 14 plus 9 is 23. This is correct. It took me more time to check than it did to find the solution using a matrix equation. Again, that just seems pretty neat. I don't normally say this, but now might be a good time to go get a snack or maybe have a LaCroix or something, because this next part's going to really require your noodle. So see you in a second, perhaps. Cramer's Rule is another method for solving systems of equations, and it was actually discovered by Colin MacLeod and Gabriel Cramer separately around the same time. You know, no internet back then. It's useful for quickly solving 2x2 systems or 3x3 systems, but it wouldn't be much use for higher order systems because of the time that it would take. So let's consider the following system. 4x minus 2y equals 10, and 3x minus 5y equals 11. Recall from a couple minutes ago, or several days ago, or just now, that these matrices can be used to represent that system. We have the coefficient matrix, the variable matrix, and the constant matrix. So it's very important to know what the coefficient matrix is, and then also to know what the constants are. So to solve by using Cramer's rule, you just need to compute 3 things. 1, the determinant of the coefficient matrix. So this would be negative 20 minus negative 6. Negative 20 minus negative 6, negative 14. Then the determinant of the coefficients with the x coefficients replaced by the constant matrix. So that would look like this, replacing the x coefficients with 10 and 11. And we're going to find the determinant of that. So that would be negative 50 minus negative 22. Then we're going to do the same thing, but we're going to do it with the y coefficients. So this time it would be 4, 3, 10, 11. So that would be 44 minus 30 which is negative 14, positive 14. So our x value for our system is going to be that x determinant divided by the original determinant, which is 2, and our y value for our system would be our y determinant, 14, divided by our original determinant, negative 14, which is negative 1. So this tells us that our solution is 2, negative 1, which we can see pretty quickly is correct. So this is a really easy way to solve a system of equations. So Here's a summary of that, a little bit neater if you need to see it. Here's what I'll leave you with. Go ahead and give this a try. See if you can do these two systems on your own, and then we'll figure out how to do this for a 3x3 system. Thanks for watching. I hope you found this helpful. Have a great day.